Hello all, welcome to this course on time series modeling and forecasting using R. So now we are entering the last week of this entire 30-hour course, and then as you see in front of you, the very last topic would be some sort of a new idea here, or rather a recent idea, which is machine learning integration in time series. Okay. So I can understand that probably some of you may not have a background in machine learning, but you need not worry. So the entire topics in this week would be more from an introductory perspective rather than getting deeper into each and every idea here. Okay. So we'll try to sort of develop some understanding as to what all different machine learning ideas are there which can be implemented along with integrating in a time series kind of a setup. Okay. So and on the other hand, I'm very sure that many of you might also have some understanding about machine learning already. So let's say the usual regression that you do, or classification problems, decision trees, random forests. So all these are forming a crux of what you call as machine learning. But over the next week or so, and then especially in this week, we'll focus not only on machine learning, but a few advancements of that, such as neural networks in time series, or let's say deep learning ideas in time series, and so on and so forth. Okay, of course, depending on time. But I've kept this at the very last because this is not kind of introduced in a traditional time series sort of a course, but due to the demand of recent times, or due to the integration of this entire idea about, let's say, ML or artificial intelligence in general, or deep learning, neural networks. So I thought of putting at least some topics and giving some flavor about integration of ML into the time series domain. Okay. So again, the first session would be, again, like I said, more from an introductory perspective. So we'll try to understand different ML ideas which could be implemented in a time series framework. And of course, as we'll go deeper into the week, we'll try to sort of focus on some individual ideas, let's say regression more, or random forest, decision trees, etc. And then try to see some applications of that into time series, and so on and so forth. And of course, there'll be one session particularly about neural networks. So there I'll try to explain a bit about neural networks from scratch. So again, if nobody is sort of very familiar with the idea of neural networks, and of course, we'll try to integrate neural networks into time series by developing one very famous model which is called as neural network autoregressive model. So of course, all of that would sort of follow, but the first session would be more from an introductory perspective. Okay. So we'll start this broad idea about machine learning in time series, and a very small introduction to start the things off with. So machine learning models have gained popularity in time series analysis due to their flexibility. So a couple of points here. First is flexibility and ability to capture complex patterns. Okay. So again, I'd like to pause here and then probably go back towards, let's say, some of the initial sessions of this course, and then try to understand that where all we started. So we started by developing some very basic time series models. So again, all of you, if you remember, so let's say autoregressive, moving average. Then we sort of integrated or sort of combined AR and MA into ARMA, then ARIMA, SARIMA, right? But one particular feature there was linearity. So we sort of assumed very strongly that, let's say, the time series is linear, or at the most it can be transformed to a linear sort of a setting, right? But again, many practical examples are of course not linear. So linearity goes for a toss, right? And then how do you capture non-linearity? So of course, in the last few sessions we've discussed non-linear time series as well. So if you remember, we discussed about threshold models and so on and so forth. But what next, right? So let's say if you have like really complex patterns, then of course all these models may not do good, and you require some sort of a black box method, right? So the entire idea about machine learning, we should always understand that ML is always a black box kind of a method. So what do you mean by black box method? So black box method means that if you give the ML model or ML technique some inputs, then you actually don't know that what's going on inside the model, right? So you can't explain what the model is. So let's say decision trees, random forest, or support vector machines, right? So you can't really enter into the model setting and then try to explain each and every point, and hence it's a black box. So you don't know what's going inside the modeling sort of the arena. And if you throw in some inputs, then the ML model has to give some outputs, and the outputs are what you visualize or what you see towards the end of the day, right? So in that sense, the entire area of ML has its own pros and cons. So why pros? Because it's able to very well manage the complex patterns as written here. But at the same time, if you want an explainable model, or if you want to see more in depth as to what's going on inside the model, then you have to step back a little bit and then really try to sort of explain it using some traditional time series models, or be it linear regression sort of a model, and so on and so forth. Okay. So, this idea of black box one should always understand, not just for this course, but let's say if you are sitting for any other ML course or introductory ML course, deep learning course, neural networks course, or data science course. But the crux of all the ML models are that the ML models are nothing but black box models. Okay. Alright, anyway, so again just to repeat the first point, that ML models have gained very much popularity in time series analysis due to their flexibility, and on the other hand the ability to capture some complex patterns. Okay. And secondly, depending on the nature of your data and task you want to achieve, you can choose among several models. So again, ML, as we discussed a short while back, that a lot of models sort of form the crux of the ML model, sort of an umbrella, and then you can choose among several models, each with its own strengths and weaknesses. So each ML model, let's say regression, classification, SVM, random forest, decision trees, etc., each come its own pros and cons. So the following slides will cover the different kinds of models initially which one can develop, and then how do you integrate each and every model into a time series sort of a setting. Because again, at the end of the day, so you should not forget that the data we have is nothing but YT sort of a data, where it depends on the time point. Okay. So how do you sort of pick up any practical time series data, which is let's say YT, YT plus 1, YT plus 2, etc., and sort of apply some of the well known or traditional ML models to sort of integrate the two. Okay. So what exactly are all the classical ML models or classical machine learning models? So we'll again spell out a few. So let's say these models are often applied with feature engineering techniques, right? So again, don't worry. So we'll try to explain what you mean by feature engineering techniques, where lagged variables, rolling statistics, or Fourier transforms are used to create the features. So again, I'll pause here for a second. So again, many of the terms or terminologies might be new to many of you. So let's say features. So features is nothing but independent variables, or nothing but the inputs that you throw inside the model. Okay. So this is a very classical sort of a terminology pertaining to ML setting, that features are nothing but all the independent X variables or independent inputs that you sort of input in the ML model. Okay. Now, how do you apply the feature engineering techniques, or by the way, what exactly would be the features, right? So these are some of the ideas. So let's say lagged variables, so xt minus 1, xt minus 2, x3 minus 3, etc., or rolling statistics, or at the same time Fourier transforms are used to create all these features. Now, what exactly are these? So let's say linear regression. So again, I'm very sure that almost all of you should have some understanding about linear regression, right? So linear regression forms the base of any of the advanced ML models also. So linear regression, how do you use them? So used for forecasting when the relationship between the dependent variable, let's say y, and its lagged variables is linear. Okay. Now again, one important point to note here is that if you are sitting in a non-time series kind of a course, or if you are sitting in a regression course, then these lagged variables would be nothing but the independent variables, and this is nothing but the x variables, right? But since we are trying to integrate the regression idea into time series, so what we can do is we can have, let's say, one dependent variable which is yt, and one very easy thing to achieve or sort of get all the independent variables is simply look at all the lagged variables of yt. So yt minus 1, yt minus 2, etc. Okay. So all these would be my independent variables, and of course yt is the dependent variable. Alright. So this is a very easy sort of a integration or sort of a link between a linear regression model and a usual time series setting. Okay. So again, linear regression is used for forecasting when the relationship between the dependent variable and its lagged variables is linear. So again, linearity is sort of the important aspect here. If linearity is not met, then again you have to go for some of the advanced ML models and so on and so forth. Now, second would be SVM. So full form of SVM is support vector machines. So again, these are applied in time series classification and regression tasks, especially with non-linear relationships. So again, anything apart from regression, you are slowly entering into the non-linear setting, okay, one by one. So again, the another important terminology here in this slide is classification. So classification stands for, let's say, if your dependent variable is a binary variable, let's say 0, 1. I can give you some standard examples, let's say yes versus no, or males versus females, right? Or again, let's say high versus low, something like that. So whenever the dependent variable has categories which are only 2, then this is a classification problem, or rather a binary problem. Okay. So support vector machines are applied in time series classification problems or regression tasks, but especially with non-linear relationships. So if you want to explore more in a non-linear sort of a setting, then of course linear regression won't be useful, right, since the term itself contains linear. But as I said a short while back, one can actually explore some of the advanced techniques, let's say SVMs or random forests, gradient boosting, etc. Okay. And thirdly, random forests and gradient boosting. So all these are capable of handling non-linear relationships again, right. So I should highlight that effectively and perform well with engineered lag features. All right. So this is a small example about random forests, gradient boosting. So these are capable of handling non-linear relationships effectively and perform well with engineered lag features. And some of the examples might include some, let's say, highly non-linear time series structures. Okay, so let's say if a time series structure is highly non-linear, so linearity goes for a toss, right? So you have lots of ups and downs, lots of complex patterns, lots of, so you have a trend plus seasonality plus, and again trend is not a continuous trend. So let's say it's upwards then downwards, right? So let's say you have a highly non-linear sort of a time series, practical time series, then of course linear regression might not be useful. SVMs might not be again useful. So you maybe require some ideas like random forests or gradient boosting, etc. Now on the other hand, we have a plethora of different models which connect the neural networks idea to time series, and again as I said a short while back, you need not worry, there would be one extra session, not extra, there would be one session this week pertaining to only neural networks integrating with time series. Okay. So what exactly are neural networks? So again, deep learning models are useful for capturing non-linear dependencies and again complex temporal structures, right. So again neural networks, they are capable of handling non-linearity very well, and again temporal. So again this is a slightly newer terminology, we did not use this quite often in the earlier lectures. So temporal means anything that depends on time. Okay, so if something varying temporally or if something varying across time, we sort of say that you have a temporal sort of a structure in that. And these are some of the very well known or well applied neural networks in literature. So the first one is recurrent neural network or RNN, and even inside the RNN we have these two which is very widely applicable ones. So first one is LSTM or long short term memory, and then these are effective for long term dependencies in sequential data. So let's say if you want to preserve the memory inside the neural network method or methodology, then one can actually go with a LSTM sort of a structure or long short term memory structure. And on the other hand, let's say GRUs. So GRUs mean gated recurrent units. So GRU is a simpler alternative to LSTMs with comparable performance in many cases. So again, just to repeat that, you need not worry at all as of now. So I am just trying to give you that what all ML techniques or what all deep learning techniques, neural networks are there, where integration of all these ML models to a time series setting is possible. But down the line, like I said, we will explore deeply into the idea of neural networks a bit more in a different session. Okay. But again, just to repeat that these are some of the widely applicable ones when it comes to neural networks. So and then again both of these form under the, or they sort of come under the RNN. So RNN is recurrent neural network. So first one is LSTM, which is long short term memory. So if you want to preserve, let's say, memory over a longer time, then one can actually use LSTM. On the other hand, one can use GRU or gated recurrent units. Then the third one is convolutional neural network or CNN. So again we are under the neural networks heading. So the third one could be CNN or convolutional neural networks, and these are again useful for extracting local patterns from time series, especially in combination with RNN. So let's say if you want to explore more locally, so locally means in a short neighborhood, or rather than exploring for the overall time series, let's say if you want to divide the time series into batches, into smaller batches, and then extract some useful information from all these small batches one by one, then rather than applying RNN, one can actually go with CNN, okay, or convolutional neural network. And transformers. So again, I'm pretty sure that, so again I'm sure that all of you must have heard all these terminologies somewhere, right? So neural networks, deep learning, transformers, CNN, RNN, LSTM, ML techniques, random forests, etc. But again, this particular session would be again useful to give a overview or sort of an idea about what exactly all of these mean in basic terms. And later on, of course, we'll see that how do you integrate each one of them with a time series setting. Okay. So under transformers, what we have? So first one is attention mechanism. So effective for long sequence modeling, right? And then second one, when it comes to integration with the time series setting, you have a time series transformer, or in short TST. And then adaptations of the transformer architecture for time series forecasting and classification. So transformers could be used again in twofold mechanism. So one is forecasting, second is classification. So if you want to classify an object into different categories, like we discussed a short while back, then one can again use a time series sort of a transformer or TST for classification problems, or the usual regression sort of a setting to forecast. And then next is autoencoders. So what do you mean by that, autoencoders? So used for anomaly detection and feature extraction in time series. So again, I'll pause here for a second and try to understand, or try to make you understand what do you mean by anomaly detection. So again, I think we introduced this idea long back in this course when we were seeing some examples, right, of different time series applications. So and one very important application was anomaly detection. So anomalies are any situations which sort of change the usual path of the time series. So I'll give you an example. So let's say if you have a time series which is behaving like this, and suddenly you see that you have a sharp drop, right? So maybe a stock price or something like that, or let's say gas prices, right? So this could be some hypothetical example. But let's say suddenly the time series is moving like this, and suddenly you see a sharp drop, and then again let's say the time series goes up and then starts behaving as earlier. So these could be anomalies. So anomalies are all those which are slightly different from the usual pattern. Okay. So how do you detect that? So it's called as anomaly detection, then estimation, forecasting, right? But if you don't detect the anomalies, then if you simply blindly put forward an ML model or some time series model, it won't do a good job, right? Because you have to capture all these anomalies in the data. And for that, autoencoders could be useful. And again, autoencoders are inside the neural network framework also. Okay. Then the next kind of a model are called as hybrid model. So again, as the name suggests, so hybrid should be a combination of 2 or 3 different things, right? So hybrid model combines the traditional statistical models or machine learning techniques with neural networks. Okay. So on one hand, you have the traditional statistical models or ML models combined with some idea about neural networks. Okay. Now again, I try to explain a bit more as to what do you mean by statistical model. So statistical model is any model which is explainable. So let's say ARIMA or regression, right, where you can actually write down the model. So if I tell you that YT follows ARIMA, or YT has an ARMA structure or AR structure, MA structure, whatever, then one can actually write down the model using a pen and paper, isn't it? So all such models which are explainable are called as statistical models. So statistical models are not black box models, right, because you know what is going on inside the model. You know the complete model structure, you can play around with the parameters, you can estimate the parameters, right. So it's not quite a blind model, right. So all such models are called as statistical models. On the other hand, any model which is not explainable are ML models. So let's say random forests, decision trees, gradient boosting, SVMs, etc. And the third idea is neural networks, which we just discussed. So any sort of a combination between statistical techniques or statistical models or ML techniques with neural networks are called as hybrid models. And all these are sort of a standard example. So first one could be ARIMA plus neural networks. So combines the statistical models, let's say ARIMA, with neural nets to capture residual patterns. So again, the idea is exactly same. So why would one want to combine all these? So let's say if you want some explainability in the model. So if you don't want a completely black box sort of a model, then why not just combine them, so that you have some, you have room to play around with some explainability and black box sort of a output, right. So you're introducing or rather combining an ARIMA setting which is explainable along with some of the advanced neural network setting. So you can actually explain the model very well using the ARIMA structure, as well as try to capture the non-linearity in the existing model. Okay. Because again, just to repeat, that ARIMA cannot handle non-linearity very well, right. So if you combine ARIMA with neural networks, you get a strong sort of a hybrid model. So again, combines the statistical models, which is ARIMA in this case, with neural nets or neural networks to capture the residual patterns. Second sort of an example would be CNN RNN hybrids. So use CNNs to extract the features from the input and RNNs for temporal modeling. So again, this is a combination of CNN and RNN. So one can actually use the convolutional neural networks to extract the features from the input, and one can use the recurrent neural network for temporal modeling. So temporal modeling is nothing but time series modeling. So let's say to define the actual RNN model, one can use RNN, and to extract the features and information from all the features, one can use a CNN. And third could be deep AR. So probabilistic forecasting model developed by Amazon using RNNs again. So you have a special name for that. So these models are called as deep AR models. Okay. And then deep AR are nothing but probabilistic forecasting models developed by Amazon using the same sort of an idea, which is RNN idea. Now, the next set of models are called as probabilistic and Bayesian models. So, again I will try to explain very briefly as to what you mean by Bayesian. So, Bayesian is a slightly different sort of a category in statistical models, which includes a prior information. So, whenever if somebody is saying Bayesian, right. So, Bayesian always relies on some prior information. So, what do you mean by prior information? I will give you a very simple example. Let us say you want to estimate a simple parameter theta, right. So, again forget about time series for the time being, right. Let us say the idea is to estimate this unknown parameter theta, and for some reason you know some information about theta. So, that information is called as prior information, usually using some historical studies or some other, let us say, news, for example, right. So, you have some prior information about this parameter theta. So, how do you apply or how do you use this prior information and the likelihood of the data that you have to get some idea about theta? Okay. So, this route, that using some prior information, how do you improve the estimation of theta, is called as Bayesian school. Okay. So, any sort of a Bayesian technique or Bayesian estimation technique, Bayesian forecasting technique, Bayesian predicting technique always makes use of some sort of a prior information. Okay. So, on the other hand, we have probabilistic and Bayesian models. What do you mean by that? So, probabilistic approaches provide uncertainty estimates in forecasts, and these two are widely applicable. One, so first one is Gaussian process. So, non-parametric models suited for smaller data sets are called as Gaussian processes, and on the other hand we have Bayesian structural time series, or in short BSTS, useful for modeling trends, seasonality, causal inference, etc. Okay. So, again what do you mean by probabilistic and Bayesian models? That it sort of uses some prior information first. On the other hand, there should be some defined probability. So, when it comes to Gaussian processes, this term Gaussian stands for a normal distribution, by the way. So, normal distribution, the other name for a normal distribution is Gaussian distribution, by the way. Okay. So, Gaussian processes sort of explore the idea about normality, but again one can actually have non-parametric models also suited for smaller data sets, but there has to be some probabilistic idea. So, one can put forward some probabilities. Okay. And on the other hand, BSTS models, or Bayesian structural time series models, which are useful for modeling trends, seasonality, causal inference, etc. Okay. Then the next set of models. So, again if you follow, we are trying to sort of explore a bit more every time and then trying to delve deeper into the advancements of all the models, right. Now, this slide gives you some specialized model for time series. So, first one is called as Facebook Prophet model. So, designed for business forecasting, handling seasonality, holidays, trends, etc. Okay. By the way, all these are specifically suited for modeling time series data. So, Facebook Prophet. Second one is NBEATS model. So, neural basis expansion analysis for interpretable forecasting. So, again let us not delve deeper into each and every model, just try to understand that what all models are there in place which one can apply or sort of deploy, right, depending on the data set we have or the goal we have, be it forecasting, or do you want to handle seasonality, do you want to handle trends, right. So, accordingly one can suit or rather pick the suitable model and work using that. Okay. So, Facebook Prophet, second one is NBEATS. Third one could be, let us say, temporal fusion transformer, or TFT. So, this one, the TFT model combines attention mechanisms with interpretable forecasting, right. So, again the basic idea is that how do you sort of move from linearity to non-linearity, then even more non-linearity, which is called as complex patterns, and so on and so forth down the line. Now, next one is called as ensemble learning. So, again many of you might have heard about bagging techniques, boosting techniques. So, all these are part of ensemble learning ideas. So, combining models often improves performance, right. Let us say bagging and boosting techniques. So, what do you mean by bagging and boosting? So, aggregating predictions from multiple models. Let us say example random forests, XGBoost, etc. On the other hand, one can have stacking. So, what do you mean by stacking? So, layering models where predictions of one serve as input to the another. So, all these models are nothing but again combination of different models, which is called as ensemble learning. So, ensemble means a combination of different techniques or combination of different models, right. So, one can actually combine some models to improve the performance. So, let us say random forest, XGBoost, or stacking. So, stacking means layering several models where predictions of one can serve as input to the other model. Now a bit more on classical ML models, and of course in the later sessions we'll delve deeper into each one of them probably, or if not each one of them, then at least some of the usual ones. But classical ML models and time series analysis rely on structured feature engineering to transform the sequential nature of time series data into a tabular format suitable for all these algorithms. So let's say linear regression, decision trees, random forests, gradient boosting models, k nearest neighbors. So far we did not discuss about k nearest neighbors. SVMs we discussed very briefly, right? K means clustering techniques, naive Bayes. So by the way, under the ML umbrella or ML models, you have two different kinds of models, right? So one is supervised, the other is unsupervised. So supervised means that if you have labeled data as inputs, it's called as supervised models. Or unsupervised models is where the inputs are not labeled, so you don't know that which input belongs to which category. So clustering techniques are usually unsupervised ML models, and all the other ones, so linear regression, decision trees, random forests, are supervised models, because the inputs that you have or inputs that you feed the ML model or ML technique with are all labeled data sets. Okay. So probably I'll stop here for this session, and again we'll pick up some of the widely applicable ones in the next session, and then try to sort of delve slightly deeper into each one of them. Let's say regression, decision trees, random forests, at least some of the well known ones. Okay. Thank you.